here we go, the classic postal service problem. Okay, so we want to maximize V equals XYZ because it's a rectangular box, subject to the constraint, and the constraint is that length plus girth is less than or equal to, what did I go with, 84?
Yeah.
Okay, 84. And so we decided, let's make this, we'll write it as Z plus 2x plus 2y less than or equal to 84. And again, the picture that I had on the board for you guys was, here's my package. And so if I call this, x and y and z, the girth of the package, this 2x plus 2y is coming from you take a belt and put it around the package. And so however long that belt is plus z has to be less than or equal to 84. And I don't know. I remember the original problem being 108. That was actually, I think someone just wanted nice numbers, so they changed it to 84. Although 108 is not bad either, I think. So anyways, how's this work? The idea is this thing is the objective function. And the other thing is called the constraint. And so what I'm going to do with the constraint, okay? So I guess, if I'm really trying to maximize the volume, first of all, you have to understand, I know this says inequality, but why would you go make the girth smaller than 84? You wouldn't, right? So what we really want, we want z to equal, and if I subtract these to the other side, 84 minus 2x and minus 2y. That's what we want, right? Because we're trying to maximize. So you definitely want to have as much girth as you can. And what I'll do now is I will substitute that into the objective function, right? So I'll take this, okay, and I'll substitute it in to the objective function. And so since z equals that, I can now write v is a function of x and y, right? I eliminate z this way. It's going to equal x times y times 84 minus 2x minus 2y. Okay? And here's where I'm interested. When I go around to the different groups, did you guys distribute that x, y, or did you leave it as is?
Distributed.
This happened. Your group distributed? How about your group? Aaron and Sullivan, you guys left it as is? Oh, okay. So at this point, we're not telling what we did. All right. So let's distribute since that's what most people did. I don't have to, right? But I will.
You have to do a product rule when you take the partial derivative.
I'm going to, yeah. So there's going to be product rule kind of stuff involved then. So, but let's go ahead and distribute, and maybe we'll avoid some of that. So let's see. We're going to write that v of xy is equal to, it would be 84xy minus 2x squared y and minus 2xy squared, right? Okay. So now I want to take the partial derivatives, right? And so let's see. I'll do the partial of v with respect to x first. Okay, the partial of v with respect to x. So that means I'm treating y as a variable. Question, Kevin?
We just have to know, is it 14, 14, 20? We're dying to know.
I know. I can't wait. I know. I can't wait. Well, I heard it there. All right, we'll see. So let's see. 84y minus, and y is a constant here, so I could just pretend the 2y is a constant, so which it is. Okay, so this is 4xy, right? And here the y squared is a constant, so just the x kind of goes away, so minus 2y squared. There's dv dx, the partial of v with respect to x. And so I'll also do the partial of v with respect to y, and, well, it's funny because by symmetry you could just write the same thing and just switch the roles of the variables. It's going to be 84x minus well, this is interesting. It's going to be 2x squared, and then this will be minus 4xy, right? Okay. So then what I do is I set these things equal to 0. Why? What am I looking for here?
Critical points.
Yes. We get critical points or critical values. Critical points are where what happens? Both partials equals 0, or where either partial, do you know why I'm writing the rest of this? What's the other what other way you can get critical values? If either partial is undefined, you get critical values. That's right. Now, in this problem, I understand that doesn't matter because these are polynomials. They're defined no matter what you put in for x and y. You can compute it, right? But if you had fractions or square roots or other things, the domain issues give you other critical values. Anyways, this is what I have. And so I have kind of a system of equations. And that's what you have to do is you have to solve the system of equations. And of course, you know, when you see this and it's kind of quadratic and set equal to 0, I hope you thought of factoring. That's what you want. Your algebra instincts should be, oh, I can factor. What kind of factoring do I always try first? We always try GCF first, right? So let me do some GCF factoring here. So let's see. If I factor out of the first one a y, I have 84 minus 4x minus 2y, right? And then here I have x times 84 minus 2x minus 4y. Okay, equals 0. And so now you have these equations set equal to 0, and I want to point out that there is a critical value. You're going to get critical values if x equals 0 or if y equals 0, right? But this is boring. Well, maybe it's interesting, right? What happens if x or y is 0? How much volume are you going to have? Right? The volume is going to be 0 because it's x, y, z. So that would be your minimum. You can minimize the volume that way. We're interested in maximizing the volume, and so I'm thinking, all right, what I really want is I want the stuff in parentheses to equal 0. So I want 84 minus 4x minus 2y to equal 0. And I want 84 minus 2x minus 4y to equal 0. Let me do one more step here. I would probably rewrite the system this way. Maybe I would write 4x plus 2y equals 84, and then 2x plus 4y is equal to 84. Okay? And you are in algebra now, right? So back in algebra, you learned how to solve this. And I agree with Kathy that if you know how to do algebra, which I refuse to put in a Calc 3 class, I will tell you you should be able to come up with x equals 14 and y equals 14. Right? Once you have that, then what? Come back up here, right? And so z is 84 minus 28 minus another 28. And so z is equal to 84 minus 56, 28. That's really cool. Right? So this is a beautiful shaped package to maximize the volume and avoid the charges. Okay? And you could, of course, multiply that out if you want what the volume actually is. But this is a classic problem. So yeah, I just wanted to show this work here.
You're going to give us something ridiculous to do on the test. You're not going to give us an actual
I always try to make the tests impossible.
Right.
That's my goal, right? It's pain and suffering, right? I make the homework easy and the tests unbearably hard. But anyways, this problem here, so yeah, this is the second partials test at work, and so we did, when you multiplied this times this, you got 16xy, and then you got the same thing. Well, we knew that would happen, right? Because we know that we usually get the same thing here and here, and so you add 16xy, and then you plugged in your 14, which is our critical value, and you showed that this is positive, right? That's what this
No,
is?
it's up above.
Oh, no, it's...
Yeah, that is right there, yeah.
That's it, right? So the point is this is positive. And if it's positive, we know that this point is either a relative max or a relative min. And how do we figure out what kind it is? Well, I tell people, just look at that part, right? Because what is this? This is what you might call Vxx, right? The second derivative with respect to x twice, the second partial with respect to x twice. And so if I look at that, and I plug in 14 for y, I notice that this is negative. And let me just go back to the world of Calc 1. If it's negative, that means concave what? Second derivative negative is concave down frown. And so that proves we really did find a maximum volume of 5488. Nice. Yeah, thanks for showing us that. That's nice. Let me ask you guys, when you do this problem we just did, what's harder, the calculus or the algebra? I propose that for most optimization problems, the algebra is more difficult than the calculus. This is a classic problem because it's not too bad. But when it comes right down to it, what it all came down to, and I didn't show this algebra, is you had to solve a system of equations, right? And we only have two partials here. There's going to be other problems where you have more partials to think about, like if you added another variable, you'd have 3. And so the systems of equations are tricky, okay? And, well, I guess there's other issues. Sometimes even figuring out what the constraints are and how to simplify, that could be tricky also. So anyways, this is your example, another example of an optimization problem in X and Y. When we do this problem using LaGrange multipliers, we are going to up the volume function a dimension. We're going to go one dimension higher. But then we gain some benefit from it. So it's kind of interesting how that all works. So let me do that on the next page here. So here's a theorem. And the idea is, what we're really doing here is section 14.9, the method of LaGrange multipliers. And so the theorem, which we can prove, is let f of xy and g of xy be continuously differentiable. Now, these words here, we mentioned them in the earlier sections of the chapter, but we certainly didn't harp on them. I mean, I talked about continuity before we took exam 1. And so here I'm saying that we want all the partial derivatives to also be continuous, okay? But let me just say that for problems like the one we just did, where you have polynomials, that's going to happen, okay? You might just say, in parentheses here, suppose f and g are nice functions. So most of the functions we encounter will be continuously differentiable. Okay. So then, if the max or min of f subject to the constraint g of xy equals 0 occurs at a point AB where I shouldn't say then here. I should just start with if. This will be more clear. If the max or min of f, subject to the constraint g, occurs at a point a, b, where, and now what does this mean? That's the gradient of g evaluated at the point a, b, and we want that to be non-zero. Okay? Then, and here's the conclusion. So here's the if, all this stuff. Then, here it is. The gradient of f evaluated at AB must equal lambda times the gradient of g evaluated at AB for some lambda, which is going to be a real number. So, have you guys seen this Greek letter before? Lambda? It's the lowercase l, let's say, for Greek. And it's funny because it's used several different places in mathematics. If you guys met me on Tuesdays and Thursdays for linear algebra, right after spring break, actually no, next week, they're going to start learning about lambda, which is called an eigenvalue. This is a different lambda than that. So none of you guys are in there, so that's okay, but you may encounter that lambda someday. But this lambda is probably because it's LaGrange that this is named for, so they used L. This is called a LaGrange multiplier. Okay? So, what happens is, the theorem tells me that lambda has to exist. Right? And also what happens is, I'll end up not having to solve for z in the constraint and then put it into the v. I'll avoid that step. But what'll happen is I'll get a system of equations to solve. Because, you guys, what kind of equation is this? This is a vector equation, right? Because we have that gradient thing. Gradients are vectors. They're vectors of partial derivatives, right? I mean, what does gradient of f even mean? It means, well, df dx is in the first coordinate, and what else? Df dy is in the second coordinate. I'm talking curly d's here, right? So when I have a vector equation, you can turn that into regular old scalar equations also. What we really have, okay, is we have a system of equations. We have the equation f x of xy is equal to some number lambda times gx of xy. We have fy of xy is equal to that same number lambda times gy of xy. Okay. And then don't forget this equation, the constraint. That's a third equation. G of xy equals 0, we're saying. Okay? So what happens is you get equations from Lagrange multipliers. This is the Lagrange equations. And you get a third equation from the constraint. And so I have, how many unknowns here? X and Y, right? Well, I introduced a third unknown, lambda. We don't know what lambda is. But I have three equations. So I should be able to solve the system with some algebra. So I guess you have to see an example at work. And so let's go back to the Postal Service problem. So here we go. In the Postal Service problem, we had volume, right? So here comes the Postal Service problem redone. Revisit it. Let's say. So here I go. I know that my function was volume, right? So I want to maximize volume of x, y, z is equal to x, y, z, right? So there's my objective function. Oh, why did I put commas? Sorry about that. X, Y, Z. That's the product of them. Okay. Subject to the constraint. So how did we write the constraint last time? Well, last time we wrote it was 2x plus 2y plus z had to equal what? Okay, let me write it this way. Minus 84 has to equal 0. Okay? So this I'm going to call g of x, y, z. Oh. So g of x, y, z equals 2x plus 2y plus z minus 84. And I'm going to have that equal to 0. Okay. So there is kind of an issue here. The issue is this. At least this may be an issue for you. I don't know. If you're trying to follow along from this theorem, what everything is, the problem is I gave you the wrong version of the theorem because g here is just a function of x and y, and f is a function of x and y, and so this theorem is true, right? But it's also true that it's true in higher dimensions. So let me show you the book for just 1 second. See, procedure, method of LaGrange multipliers in 2 variables. Let me turn the page. So this is actually page 970 of your book, or no, 971. LaGrange multipliers with 3 independent variables. Look at the procedure box. It says grad f is equal to lambda grad g. But notice how it's x, y, and z, right? So how does that change things for us? Well, what it really means is how many equations am I getting from the Lagrange multipliers? What does grad f of x, y, z mean? It means there's some vector with df dx, df dy, and what? df dz. So we're going to get another equation, all right? So maybe what I'll just do is say, in the 3D version, you also have fz of xyz is equal to lambda times gz of xyz. And that's what's really going on in this problem. Okay. Like I said, if you choose to use Lagrange multipliers, you're actually going to be up a world in the number of dimensions. We're going to be in the world of R4 here. We have x, y, z, and lambda all involved in this problem. But it's kind of cool how it all works. Here we go. So the constraint, right, that's this. I guess for us, in the 3D version, the constraint is g of x, y, z is equal to 0. So one equation I have is sitting right here, right? But the other equation that I get is I need to take grad v and set it equal to lambda grad g. Okay? So again, that's really 3 equations in one. That's really vx equals lambda gx, vy equals lambda gy, and vz equals lambda gz. That's really what's going on here. Right? When you write a vector equation, you're writing lots of equations at once. So here I go. Let me turn that first one into an equation. So what is Vx? It's yz. So we get y times z is equal to lambda times, now what would be gx in this problem?
2, 2, 1. 2.
Just 2. Why just 2?
Because X is
We treat all these things as zeros, right? Now when Kathy's talking about the 2, 2, 1, I think you're jumping ahead and doing like gy and gz, right? You're right. This is going to be a 2, and this one's going to be a 1 when I take gz. Let me complete the system of equations here. What would be vy? Well, that's pretty easy. That's x times z, right? And what would be vz? xy. And so there's my system of, well, here is my system of equations. I have the constraint, and I have 3 other equations. So now the trick is, what do? You have to do algebra, right? So sometimes LaGrange multiplier is an issue, is going to be the algebra. But in terms of coming up with the equations, it kind of makes things easy. There's no substituting. You just take your constraints. Got to be able to take the gradient of it. Take the objective function. Got to be able to take the gradient of that. All right, so what do? Well, how did I solve the last one? Here, let me go back to that problem. I guess I do better talk about algebra a little bit. It is more algebra. It is more algebra. You're right. You're right. Maybe it's less starting algebra, but now you have some serious algebra, right? Anyways, back to this problem. How'd you guys do this one? Can you just... So you did substitution. That's a nice way to do it. Are there other techniques you guys know about? Okay, that addition or elimination. My linear algebra students wouldn't do either of those. They'd probably use a matrix and use what's called Gaussian elimination or reduced row echelon form. Anyways, they've used matrices for this thing. All right, and I will say that once you guys learn your matrix stuff, you might go to that for this kind of problem. But I agree. We're going to either use substitution or elimination. So how does substitution work? Well, you know what I do? I try and look for, look, guys, take those first 2 equations, right? Doesn't this kind of tell you, you have yz is equal to 2 lambda, right? But you also have that 2 lambda is equal to what? X times z. So you got to start doing things like that. Matter of fact, I can already tell you that lambda is equal to yz over 2, and it's equal to xz over 2. Isn't that cool? Who cares what lambda is, though? I made it up. Right? Lambda doesn't represent anything. It's some number. So that was kind of useless, I guess. All right, so... Well, no, it wasn't useless. Because if you... Okay, so since it's kind of who cares about lambda, let's get rid of that for a second. But look at this equation. Yz over 2 is equal to xz over 2. Doesn't that prove something? Yeah, multiply both sides by 2. Divide both sides by z. And wasn't that true in the final answer? They were both what? 14. I think we're almost there. Well, we know they're equal. Now, how do we get the actual value now? Well, how about, let's see. Oh, we didn't use this equation yet, right? What's that equation tell me? That tells me that x times y is equal to lambda. Right? But what do I know about x and y? They're equal. So x squared is lambda. So what's x? Square root of lambda. All right, so it's the square root of something. Okay. Wait a minute, there's another equation I haven't used yet. Which one is it? The first one. See that first equation? One thing you'll notice about that first equation, there's no lambda anywhere in it. Right? But I know that x and y are each the square root of lambda. Do I know anything about z? Well, let's take one of the equations with z. We have, give me an equation with z, guys, any one of them. Okay, xz equals 2 lambda. Let me work with that. So if I know that x times z is 2 lambda, what should I do next? Well, the square root of lambda times z is 2 lambda. So let's divide both sides by the square root of lambda. What does z equal? 2 square root of lambda. So x is the square root of lambda, y is the square root of lambda, z is twice as big, which we remember that also, right? So we really are close. Again, I haven't used the constraint. Let's use the constraint. All right, so the constraint was, again, let's see, 2 times x. What should I write instead of x? Square root of lambda. Plus 2 times y. What should I write instead of y? Square root of lambda. Plus z. What should I write instead of z? That one's 2 square root of lambda. All that equals, oh no, minus 84 equals 0. So I have 6 times the square root of lambda minus 84 is 0. So the square root of lambda is equal to, what's 84 divided by 6? 14? Oh, cool. That's what x is. And y, right? So x, y are equal to 14, and z is equal to 28. And I guess if you really cared, you have lambda's 196, but who cares? Isn't that weird? So we threw another variable into the mix. I agree with Sullivan. We did get some pretty challenging algebra to do. But it's just substitution method right now. Or if you had matrices, boy, you could just lickety split. But you guys didn't take that yet. All right, so anyways, this is an example of LaGrange multipliers. Okay. After break, we could decide, do we do that, or do we go over homework, or both? We'll see. Aaron, you have a question before we do?
Are those matrices easy to learn?
Oh, yeah. You just have to take linear algebra.
I mean, is it like the beginning of linear algebra, or is it like...
Yeah.
They're
Yeah.
not hard.
They're not hard.
They're not hard.
No. Here we go. The open top box problem revisited. So what did we have? We had to... How did this one work? Weren't we trying to minimize when we did this? You said maximize?
Oh, no, we were trying to minimize the surface area.
Oh, okay. Minimize the surface area. So let me draw the box, and let me put that hole in there again. Okay. So again, it was open, right? And so there it is, right? And so the problem was minimize the surface area we just called S. S equals what? I think the way we did it, I think this was X and this was Y and then the height was Z. So it was
2xz plus 2yz plus x1.
right, we had XY was just by itself because we had no top, right? So XY, but then the XZ is the front and also the back, right? So we had 2XZ and then also 2YZ, okay? So that's what we're going to minimize. Subject to the constraint. Now, I didn't give you a number when we did this problem, right? I just said we want to hold a certain volume V, right? So the constraint was XYZ equals V, right? So please understand, when you do a Lagrange problem, you have your objective function, that's fine, right? So again, I have, S of x, y, z, right? That's the objective function. So again, S of x, y, z is equal to xy plus 2xz plus 2yz. But when you talk about the constraint, if you're going to do a LaGrange multiplier problem, the constraint must be set equal to what? 0. And I don't have that here. So I'm going to write, I've been using G for the constraint, and so does your book. So let's stick with that. G of x, y, z would equal what here? Right, x, y, z minus whatever number we have for v. I mean, v's some number, I'm sure. We're keeping the volume fixed, but that's what your constraint is. Okay? So what happens is, all right, when you do the Lagrange multiplier problem, what you're really doing is you're upping things a dimension. Okay? So the equation is grad S is equal to what? Lambda grad G. Okay, so what happens here, let's see, how many equations am I going to get? Well, you get 4 equations, okay? One equation you get by setting the constraint equal to 0. So this, right, set that equal to 0. And so we get x, y, z minus v equals 0. That's one equation. Why did I put commas? Sorry. X, y, z minus v equals 0. That's one equation from the constraint. The other 3 equations we're going to get come from here. Let me write them down. So let's see. The first equation would be the partial with respect to x, right? So we're going to get, Sx is lambda gx. We're going to get Sy is lambda gy. We're going to get Sz is lambda gz. So let me do that. Sx would be y plus 2z. That has to equal lambda times yz. There we go. And you can do the same thing for Sy, and you get x plus 2z is equal to, well, gy would be xz, so this is lambda xz. And then the last equation I get, Sz equals lambda gz. So that means, let's see, what's Sz going to be?
2x plus 2y.
Yes, 2x plus 2y, right? Is equal to, and this would be lambda xy. Okay. So I guess I better, maybe I should number, you guys see there's 4 equations, right? 1, 2, 3, 4 equations, and 4 unknowns. The 4 unknowns are x, y, z, and lambda. And so we should be able to solve for them.
Are you able to do that with having a b in there instead of some number for b?
I can. Can you?
No.
Oh. Put a number in
Now
there.
it's like 5 unknowns.
Yeah, but v is some volume.
Treat it like that.
Well, we did it last time successfully. No one complained. You were here last time, Kathy?
I was just like,
Okay.
I'm not complaining, I'm just asking.
I didn't mean that. Okay. Too much. So let's see. Why don't we look at equations 2 and 3? because I notice they're very similar, right? So let me subtract them. So I subtract equation 3 from equation 2. And what happens? Well, I guess I get y minus x is equal to, you see what happens if you factor out the lambda z, you get lambda z times what? Y minus x. So that's kind of nice, right? So maybe I'll bring this y minus x over here. And so I'll say 0 equals, no, 0. I want to subtract it to that side. So I get lambda z y minus x minus the quantity y minus x, because then I can factor out y minus x. What's that?
Yeah, that means that lambda z is 1.
Yeah, because, well, or, right? So let me go slowly. Lambda z minus 1 times y minus x. So you're right. I mean, one possibility, if this factor equals 0, lambda times z must equal 1 then. Or, what's the other possibility?
Y equals x.
And if I remember the open box problem, didn't we figure out that x and y had to be equal? So I think this is what's going to happen. Or lambda times z is 1, I guess might happen. So this one would mean lambda is actually, I feel like I did something wrong here, guys, algebra.
Oh yeah, then can't you log into equation 4 and just substitute in x for y?
I solve both those for lambda, and I get similar stuff, but at some point I can get rid of these
Yeah.
and get just x equals y.
We got x equals y here.
Yeah.
So, fine. I think what we should do at this point is probably use another equation. Well, like equation 4 is striking me at this point. Because if I know that x equals y, let's see, what would equation 4 say? It would say, right, so equation 4 tells me now that 2x plus 2x, because x equals y, if I'm in that situation, equals lambda times x times x. So 4x equals lambda x squared, right? So what does lambda equal then? I guess it equals 4 over x, right? I feel like I'm missing a negative sign somewhere. Not sure why. No, it doesn't matter. This is fun. So lambda is 4 over x. We also have that lambda is equal to 1 over z if we go this route. Okay. What equation have we not used yet? Well, we haven't used the constraint. What about the Let's go back to, remember we subtracted these equations? Let me write equation 3 again. So equation 3 said x plus 2z equals lambda times x times z, right? Let me show that a little better. Sorry about that. I guess one thing to tell you guys, in LaGrange multipliers, remember that lambda is the variable I don't really care about, right? So it ends up being a good thing if you can actually get lambda by itself, like I did here. Remember I got lambda squared over x? Because if I have that, right, then I can substitute into an equation, and I just get equations then that have x's and y's and z's, and that's kind of nice when that happens. I guess my point is, this is a good situation. So as you're doing the algebra and trying to navigate it, it's a good situation when you can eliminate the Lagrange multiplier. Okay? I think from here things should go a little smoother. Let's see. So we have x plus 2z is equal to, now when I shove in the 4 over x there, I just get a z, right? 4z, yes. 4z. That's even better. Because then what does x equal? 2 times z. So I think this just about gives you everything, right? If x and y are equal, and I guess you could say z is half of x, right? So I don't know which way we wrote it last time. But what it comes down to is, you know, if you want to minimize the surface area, you get a box that looks like this. You say x times 1/2 x. Those are kind of the dimensions you need, right? So if you multiply these things together, you get the volume. So I think we said, yeah, so it would be x cubed is equal to 2v, and so x is the cube root of 2v, and so is y, and then z was 1/2 of that. So z is half the cube root of 2v. And so I guess I'm basically there at this point. Right? That's what we wanted. So if we had a number, Kathy, we'd have numbers for x, y, z. That's the only difference. Okay. So this is least squares approximation. And tell you what, okay. So here's the idea. Let me show you what the book does with this, because I thought this was kind of nice. So they talk about it on page 966 at the very bottom, but on 967 they show a picture. Okay? So see these 5 red points? Those are data points. And maybe there's a linear function that represents this line that I drew through them. It's called the regression line. I called it linear regression. The method of least squares is how mathematically you come up with the best fit line. Because is there a line that goes through all these points? No. But could it be that these points are described by some linear relationship? Could be. It's just that there's a little bit of error. See, what we really want to do here is we want to pick the line, and there's lots of lines, right? I mean, I could say that this line, my pen is better than that blue. If you notice, my pen is not quite as steep as the blue line, right? Maybe I think my pen is a better fit. Of course, it's hard because my pen's too thick, right? I'd have to draw something here, but I don't really want to. But whatever I draw, somehow I want the line that gives me the least amount of total error. And as I'm looking at the line they drew, their line fits the first data point really well. The second one pretty well. Not the third one and fourth one so well, although they kind of counter each other, right? And the fifth one pretty good. So maybe it really is the best fit line. And your calculator can compute the best fit line. We could show you how to do that, or your computer. But how does it do it? Well, you can know how now that you're in Calc 3. So let me show you. Okay? And then if you really want to know how it works, come take linear algebra. Because there's more to the story. Okay? So here's the game. We want to somehow minimize what I called the, it's actually usually called the residual error. Oh man, why is it doing that to me today? Again. Okay, we want to minimize what we call the residual error. So again, I guess the picture is you have points, boop, 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 and you have a line that goes through them, kind of. That's the best fit line, guys. And what you're really measuring here is the vertical error. Do you see what I'm talking about? These are vertical distances. If this is the point x1, y1, and this is the point, I guess, x5, y5, okay? How do I get those distances, okay? Here's what I'm going to write. I'm going to write this function down. I'm going to write f. I'm not telling you what the inputs are quite yet. Equals. And I'm going to add some things up. You guys okay with that notation? Sigma, right? This I is called an index. I equals 1 to what? What do you usually put at the top? N. Yeah, 5 in our case, right? In my picture here, n is 5. I'll put n so that we can make it whatever we want. And so what I want to do is I want to add up all of these distances, right? And so what's the equation of the blue line? Let me call it little f. That's why I used big F over here, because I had a plan. Little f of x, what's its equation, guys? Yeah, has to be mx plus b, right? So, like the very first point, I know the red point has coordinates. I called it x1, y1. Now let me go with the middle one. The middle one. So the middle point has coordinates x3, y3. I guess my question is, what are the coordinates of this point directly above it on the line? Well, they are x3, what?
Y minus plus 3.
Would you be okay if I said it's mx3 plus b? That y coordinate? Because it's on the line, f of x equals mx plus b. I know that x3 is the input. You guys with me? Okay. So let me explain what big F is. Big F is a function, and what you do is we want to add up these differences, right? I basically want delta y here, right? And so what I'm going to subtract, well, like here I'm going to subtract y3. I'm going to subtract yi. I'm going to subtract each of the y's from what? What do I subtract y3 from? Tell me what to put here, guys. mxi plus b, that's right. mxi plus b. And this would work, except there's a problem.
with my strategy. The problem is that look at x2, y2. You see how y2 is bigger than the line, it's above the line? So these errors would start canceling each other out. And I don't want them, I want to tally up all the error. And so there's different options you could do, but what mathematicians do or statisticians do is they say, okay, instead of just adding these up, let's square them so that you'll always be adding non-negative numbers. I mean, I guess in the best case, you might add a 0 if it goes right through the point. But in general, what you're going to do is you're going to add. Is this okay? All right. And so this, to make it a Calc 3 problem, I want to point out that what we're going to do is we're going to keep trying out different blue lines until we minimize this. And every time you try out a different blue line, you're changing M and B. And that's why this is a Calc 3 problem, because see what I'm doing? I'm trying to minimize this function. That's all I'm trying to do. Question, Sullivan?
So why don't they use absolute values? Wouldn't squaring it weight some of them differently than others?
Yeah, and it turns out, I'm going to call it technical reasons,
Okay.
that squaring works better than absolute value from a standpoint of a statistician, let's say. Okay? Although I've gone to statistics classes where you play around with absolute values, and it works. But this is better.
Okay.
For one thing, it sure is nice taking derivatives of this function compared to absolute value functions, right? For example. So let's do it. What derivatives do I need, guys? Well, I need the partial of f with respect to what? M. And then I need the partial of f with respect to b. Oh yeah. Well, you could see you could see why for homework, all right? I mean, basically what I'm doing right now, guys, I'm in the middle of this exercise, number 68. Let the equation have best fit line y equals mx plus b, right? And then show that the function of m and b, well, no, I guess you guys are doing 68 for homework. I'm doing 69 right now, where I generalize it. Here's what m ends up being, and here's what b ends up being. And I'm noticing that in 1 minute I really can't, well, not very effectively go through that presentation, right? But if nothing else, at least you have enough, I think, to do problem 68. So why did they use the letter E? Because it stands for residual error, right? The error function, see, they actually, instead of using sigma notation, they just actually worked out what these 3 points, what the errors would be, and they squared them. So you'll get to do what I'm doing with much easier notation for homework, and I think you'll enjoy that, and yeah, we'll understand least squares by the time we're done with this. So, all right, nice work today, guys.